UCS DEC 111 Lecture 9, Ports, Parameterized Design, and Handshaking. Let's go to set 1, where we talk about ports. And ports are really important because they interface the modules to each other, and they are used as a way to call each of the submodules in the program. So it really enables passing of the data in and out of a module. And, we could be thinking of them as wires between modules, but, there is also kind of direction that we could define for the ports. So the port has name, direction, the data type, which we discussed earlier, and the width, like how many bits it's going to take for that module interfaces. And the direction specifies a signal or a data flow that comes in or out of the module. So we have input, which means that, similar to a block diagram, which we drew earlier. I'm sure you guys all remember, usually how we make the module block diagram is by showing the inputs on this side. So basically, the data is flowing in from here, and then the output here, the signals go out from there. We could specify arbitrary number of input outputs for each module. Of course, the more you do that, the more complex your module could be and the more complex handling it. So it's better to have a modularized design, as we will be discussing in this lecture. But there is also this one other type of port that we have where we have in-out. So it's a bidirectional port. It could be both used as an input and output. And we will see instances of that shortly. Here, I'm just showing examples of input wire, output register, in-out wire, that is a dual port, and so on and so forth. So, it's always a good practice to determine the data type for each port, but it's not mandatory to do that. If you do not explain the data type, this will be interpreted by System Verilog as a wire. But if you specify it, you could specify input, output, or in-out as wire or logic. You could also declare output ports as a register, but you cannot declare in-out and input ports as register. However, to reduce this confusion, as we discussed earlier, it is recommended that in System Verilog, you use the logic instead of the register. When you do this declaration of the logic, then you don't have this confusion or double checking of the input ports and getting the errors. So if you do not specify input or output, the default port direction will be input. And the default port data, as I mentioned, is wire. And if you do not specify any width, it's going to assume that it's 1 bit. So now, assume that, I have a modularized design. So there is hierarchy in my design. Here I'm showing an example of a hierarchy in design where we have a module reduction and another module reduction, and a third module mux 2-to-1, which is basically a selector between them. This is of course, a very simple example just to show you the interfaces. Now I go ahead and I define my reduction OR module, which is 8-bit wire input and wire Y output, which is basically 1 bit. And now what I'm going to do is, and there is a combinational function that relates the input and output. And of course, the module is instantiated with a big module and end module. The same is true for the other modules in this design. Here I have the reduction and I begin and end it. I define the parameters. And then here we have to be kind of careful, and we will be discussing interfaces and how to interface modules and handshake between them. But of course, the easiest form is just basically try to make sure that whatever needs to come out of this module and is going to this other module is properly connected. In this particular page, we're just defining the MOX module itself, which is basically a selector between the two based on the select signal. Now, if I want to write like a higher level design which contains these three modules, what happens is that I'm going to define this with inputs with inputs to the big module, and the result, which is the output of the big module, and a select signal that is coming out here. So I'm going to define that higher level module with those three interfaces that we just described. And then, I'm going to have these local variable here, the wires, C1, C2, which are declared here. And then what we're going to do is we're just going to instantiate a module. And when we instantiate a module, we're going to say what will be the input to that module and what will be the output. And in this particular case, the input to the reduction and will be the operand 1, and wire C1 will be the output. So we're just going to go and declare that. For the second one, similarly, reduction or with operand 2 and C2. And then last but not least, I'm going to select with the select signal between this, two wires, and then the result will be the output of this module. And I'm going to do that. So this is called a position-based port connection. Position-based port connection, as we will see shortly. And what it means is that the position of the signals, like, when I'm defining this reduction and reduction, or the position of the modules is going to tell me what's going on. Let's go to a more formal definition for port connections in the next set.